Today's lesson is section 11.7, and this is some special factoring cases. All right, so the first couple examples we're going to look at here are not much different than what we have done so far. And the nice thing about them here is they don't have a number in front of my squared term there. So we have h squared plus 10h plus 25. So we're going to split this into our two binomials. Since our second sign is a plus there, we know that both signs have to be the same, and they're both going to be the same as my first sign. So they're both going to be pluses. Okay, in front of this is easy. H times h is h squared. And then for 25, we have the options of either 25 times 1 or 5 times 5. All right, well, we want those to be able to get us to a 10. So our choice here is 5 and 5. And if we check our outside and inside numbers, sure enough, we get 5h plus 5h, which is 10h. So the unique thing about this, why this is considered a special case, is because both of these binomials end up being the same thing. They're both h plus 5. So we can actually write this as h plus 5 squared, since we know from earlier in the chapter now that h plus 5 squared is h plus 5 times h plus 5. And the same thing happens if that first sign is a negative, but the second sign is a positive. So x squared minus 14x plus 49. So second sign being a positive still tells me the two signs are going to be the same as the first sign, so now they're both negative. X is in the front. Now two things that multiply for 49 but combine for 14. Well, that's 7 and 7, which is the same thing as x minus 7 squared. Okay, so nothing too new on those right there. Our next case does bring in something a little bit different. And this is when we have m squared minus 49. Now, we looked at this case a little bit when we were actually multiplying, when we were multiplying two binomials together, but not going from this direction, not when we want to factor this. So when I have something that has two terms in it like this, m squared being a term and negative 49 being a term. Okay, so this is a binomial, quadratic binomial here. The only options I have for factoring these are, one, either pulling out a greatest common factor if it has one. This one does not, okay? Or this concept of what we call difference of squares. All right, so difference meaning subtract, which is we have a subtraction sign, and squares meaning both numbers are perfect squares. All right, so m squared, obviously a perfect square there, and 49, well, it's perfect square because 7 squared is 49. So when I factor something like this, we're still going to look for two sets of parentheses. Okay, whenever I factor different perfect squares, the signs are always going to be opposite. All right, now what goes in the front are the two things that multiply for m squared. So that's m and m. And then in the back, the two things that multiply for 49, 7 and 7. And I just noticed I made my signs the same there, so let's get rid of that one in the back and change that one to a minus. Okay, so there should be opposite signs there. Now if I check my outside terms and my inside, well, m plus negative 7 is negative 7m, and 7 times m is positive 7m. All right, we see what happens here is negative 7 plus 7 is 0. And that's why that factors into that binomial with just two terms there, because those middle terms end up canceling each other out. All right, let's take a look at another example here. So we're going to have 64n squared minus 1. All right, so now again, for it to be difference of squares, each one has to be a perfect square. So this is a little different because now I have a number with what's in the front. I got a 64. Well, n squared, that piece is obviously a perfect square. 64 is a perfect square because 8 times 8 is 64. And also in the back, the 1 is a little tricky there because we never think of 1 as being a perfect square, but 1 times 1 is 1, so it is indeed a perfect square. So signs have to be opposite. In the front, okay, so 8n and 8n, so essentially the square root of 64n squared. And in the back, the square root of 1, so 1 and 1. And again, we will see if I do this and this, 8n times negative 1 is negative 8n, and 1 times 8n is positive 8n. Those cancel each other out and equal 0, which is why I'm just left with 64n squared minus 1. All right, the last example we're going to look at here is 50g squared minus 8. All right, so again, two terms has to be difference of perfect squares, or I'm factoring out a greatest common factor. Well, neither 50 or 8 are perfect squares, so this can't be factored using difference of perfect squares. But if I notice, they do both have a greatest common factor. So 50 and 8 have a greatest common factor of 2. So if I factor out that 2, we're left with 25g squared minus 4. Now I have a difference, okay, subtraction sign in the middle there. 25g squared is now a perfect square. 25 is a perfect square, as is g squared. And 4 is also a perfect square. So now I still have my 2, can't lose my 2, but now I can think of my two sets of parentheses here. Okay, difference of squares means I have to have opposite signs here. All right, in the front is the square root of that first term, or the square root of the 25g squared. So that's 5g and 5g. And in the back, the square root of my second term, or the square root of 4 here. So 2 and 2. All right, so I'm writing difference of perfect squares. The terms in the front and the back will always be the same, right? We notice on our first one, we had m and 7, both in the front and the back, just different signs. On my second one, I had 8n and 1 in the front and the back, just different signs. And in this one, 5g and 2, 5g in the front, 2 in the back, and just different signs. And again, on this last one, if I multiply my outside and my inside together, 5g times negative 2, negative 10g, and 2 times 5g, positive 10g. So those cancel to be 0. All right, so that is our special cases there. Just a couple of new things to add in to our factoring here.